Hello and welcome to the VOT session 2. It's the presentation of winners of various VOT's challenges. And I'm Yuri Matas. I will be chairing the session. And the program is on the screen. We will have 2 blocks of presentations. The first one will be on the short-term tracking challenge winning entry by Zhang Ma, followed by the real-time by Bin Yan, and finally the long-term tracking challenge by Kenan Da. So without further ado, I will switch to Zhang Ma, who will have the first presentation.
Okay. Hey everyone, can you hear me?
Yes, we hear you well.
Shall I begin?
Yes.
Okay. Hi everyone. Good evening. My name is Zhang Ma. I'm an intelligent algorithm engineer from Zhejiang Dahua Technology of China. It's a great honor here to make the presentation about our work on VOT2020 short-term challenge. In this work, we will explore how to learn point set representation for semis visual tracking. Visual tracking is a fundamental task in computer vision. Given the target region in the first frame, it aims at locating an arbitrary target of interest during a whole video sequence. Despite that, much progress has been made in recent years. The design of a high-performance tracker on VOT2020 is highly challenging due to factors including blur, large motion, geometric transformations, and occlusions. To address these issues, we first proposed a novel tracking method named RPT by modeling the target state with a file representation as a set of representative points. Then, in order to fit the segmentation mask annotation of VOT2020, we further enhance the RPT framework with a discriminative single-shot segmentation tracker called D3S to obtain a detailed segmentation map for the target region. Finally, a distractor-aware strategy is given to make better tracking decisions and to redetect tracked objects after occlusion. In the following, each component will be introduced in detail. The target state in most of advanced trackers is described with a bounding box for the convenience of feature extraction and annotation. However, it provides only a coarse spatial extent of objects and lacks the modeling capability for geometric transforms, thereby severely restricting the localization accuracy. Inspired by IP points, we propose to model the target state of video tracking as a set of representative points, which facilitates more accurate localization and modeling of object appearance. Specifically, each location on the correlation feature map is viewed as a target candidate. The target state is modeled with a set of sample points, which is uniformly initialized with the current position. Then the initial sample points are progressively refined with actual offsets in a point-wise manner. In the field of visual tracking, the target region is generally annotated with a bounding box, which is inconsistent with the point set representation. In order to utilize the bounding box annotations for supervision, we perform a min-max operation over the refined point set, obtaining a pseudo box. The refinement process is offline trained with a multitask loss for simultaneous localization and regression. Driven by these two supervision sources, the extreme and the semantic key points of tracking target are automatically learned. For the proposed RPT framework, the target estimation subnet is constructed with a shared backbone network for feature extraction and 3 parallel RP hands for multi-level prediction. In particular, features extracted from a target region and a search region are cross-correlated in a depth-wise manner. For each location on the correlation feature map, the regression hand outputs a set of offsets to refine the distribution of sample points via 2 stages, while the classification hand outputs 2 channels for foreground-background classification. The deformable convolution layer facilitates more powerful feature representation and contributes to truly understanding the visual patterns of objects. To provide high robustness against the distractors, we complement the target estimation pipeline with an online trained classifier similar to a TOM and DLL. It is modeled as a lightweight 2-layer fully convolutional neural network for efficiency. Considering that each hand outputs only a small set of representative points, tracking accuracy is greatly limited as an inaccurate pseudo-box is obtained from the sparse point set. Thus, we propose to collect the representative points obtained by each hand to construct a dense point set that is beneficial for accurate target state estimation. The proposed RPT framework is compared with recent and advanced trackers on several benchmark datasets. For VOT2018, our tracker attains the best EAO among all methods, which is 2.1% higher than the previous best result of D3S. For VOT2019, our tracker outperforms ATP, DLNet, and other SOTA methods in EAO by a large margin. Since VOT2020 understands the target region with a segmentation mask, we propose to equip the RPT framework with a modified D3S, which narrows the gap between VOT and VOS. The original D3S is constructed with 2 discriminative visual models followed by a refinement pathway. The first one is named GIM, in which backbone features are matched to the foreground-background model to obtain the target and background similarity channels. The second one is named GEM, which is responsible for target localization with DCF. Finally, the refinement pathway combines the GIM and GEM outputs to obtain a detailed segmentation map. In our RBTS framework, we replace the GEM output with the refined representative point set of RPT, providing more accurate object location and target state estimation. We further propose a distractor-aware strategy if more than one peak of classification score is detected inside the search region. We model the full history of both the object to be tracked and the potential distractors. This enables our approach to make better tracking decisions as well as to redetect tracked objects after occlusion. On VOT 2020 public datasets, our tracker achieves a EAO score of 0.539, in which the detailed segmentation map leads to a performance scan of 0.217, while tricks including distractor-aware strategy leads to a performance scan of 0.014. It demonstrates that a segmentation mask has an obvious advantage over the bounding box in the evaluation of VOT 2020. Well, this is our presentation. Thank you.
Okay, so thank you for the presentation. There has been so far no questions from the audience, so I will, okay, so there's one. What is the speed of your tracker? And I think we would like to hear about the full version with all the tricks, which is the one that has the best performance.
Sorry?
So Xiang, there is a question
Okay.
related to your presentation on the speed of the tracker. And please tell us the speed for the full version with all the tricks.
The second version of our tracker, named IPTS, attains better results on VOT 2020 for its ability to output a detailed segmentation map as illustrated in this table.
Yes, but that's not the question. The question is about speed. How many frames per second?
Okay.
How many seconds per frame?
Okay. The RPT framework runs at around 20 FPS on 1080 GPU.
Okay, but that's the RPT. This is RPTS with the tricks that slows it down, or it's still the same speed?
Yeah, RPTS runs about 8 FPS on the same.
Yeah, 8 FPS. Yeah.
Yeah.
Still quite good. Okay, so if there are no more questions, in the sake of time, we'll switch. Thank you, Xiang, again. For the nice presentation, and we'll switch to the second speaker, which is Binyan, the winner of the real-time challenge. So Binyan, please share your screen, unmute your microphone, and we are looking forward to your talk.
Okay. Hello, everyone. Could you see the slides?
Yes, we see the slides.
Okay. Hello, everyone. I'm Binyan from Dalian University of Technology. My mentors are Professor Dong Wang and Professor Huchuan Lu. My report's title is Alpha Refine, a powerful refinement module for object tracking. This work is done under the cooperation between Dalian University of Technology and Remark Holdings. This page shows the pipeline of the algorithm given the current frame. First, a base tracker is run to get an initial bounding box. Then we crop a small search region around this box and send this search region to a refinement module, obtaining high quality mask prediction. Finally, we map mask on this small search region back to the original frame to get the final results. In summary, the whole pipeline consists of two stages: robust target localization and accurate mask prediction. In each stage, we use DIMP and alpha refine respectively. Alpha refine is designed as a general refinement module for object tracking. When combined with existing base trackers, it can significantly improve their performance. We further improve it for this year's VOT challenge, but let's first look at the base version. The architecture of original alpha refine is shown in this picture. It takes SIMIS architecture, but it is quite different from previous SIMIS trackers in the following aspects. First, it uses precise pixel-wise correlation to aggregate features from the two branches and use a non-local layer to capture global context. Second, it has three complementary output heads for bounding box, corner, and mask, which can provide diverse candidate results. Third, it uses a lightweight branch selector module to choose the optimal results. It is also worth noticing that alpha refine uses smaller search region than SIMASK. To be specific, assume the red square represents the target and the blue square represents the search region. The sidelines ratio between target and search region for alpha refine is 1:2. However, for SIMASK, the sidelines ratio between the target and the search region is 1:4. The reason why we can use smaller search region is that the base tracker has already roughly located the target. So the refinement module only need to precisely predict the box or mask rather than searching around the target on the search region. To demonstrate alpha refine's powerful refinement ability, we choose 5 famous trackers: DIMP50, Atom, semi-RPM++, ECO, and real-time MDNet, and use alpha refine to refine their bounding box results. Experimental results on LaSalt and TrackingNet demonstrate that alpha refine can significantly improve existing trackers' performance, especially for trackers like ECO and real-time MDNet, which lack in precise scale estimation. The improvement is up to more than 10%. In summary, alpha refine can significantly improve existing trackers' performance. The speed of alpha refine is fast, which promises that the tracker can still run in real time after using alpha refine. Here are the mask quality comparison between alpha refine and SIMASK. The golden one represents mask predicted by alpha refine, and the blue one are predicted by SIMASK. It can be clearly seen that our mask quality is superior to that of SIMASK. Specifically, our method is more robust to cluttered background similar distractors. In addition, our masks are more complete, and the edges of our methods are much more sharp. Until now, we have introduced the base version of Alpha Refine. In this year's VOT challenge, we also make some modifications to further improve its performance. We use DIMP50 plus Alpha Refine as our baseline for this year's VOT challenge. Improvements are mainly from the following aspects. The first one is more diverse mask datasets. The second one is more powerful mask prediction structure. The third one is more robust base tracker. Here are 3 datasets that we use to train our Alpha Refine for VOT2020 challenge. Each dataset has its unique property. YouTube VOS consists of a large amount of videos, which contains various appearance change of the target during tracking period. Silency datasets feature in delicate annotations. The object's details are well retained. COCO 17 instance segmentation datasets provides tremendous instances, and there usually exists many distractors in the background, so it can improve the algorithm's discriminative power. The original Alpha Refine adopts mask prediction height similar to that of SAM mask. In the strengthened version, we replaced it with more delicate architecture that's used in paper learning fast and robust target models for video object segmentation. This further improved the accuracy of predicted mask. Recall that our pipeline consists of a base tracker and a refinement module. Except for the refinement module, the base tracker also plays an important role. In our strengthened version, we replace DIMP50 with Super DIMP. This also brings better performance due to its stronger robustness. In this page, we list every step we take to achieve the best performance. As mentioned before, we use DIMP50 plus Alpha Refine as our baseline. The EAO multi-start is 0.418. After tuning the mask threshold, we got 2.4% performance gain, and the EAO multi-start increased to 0.442. Then we introduce COCO 17 instance segmentation datasets and increase the weight of the master branch. The performance increased by 1.8%. The EAO multi-stars goes to 0.460. After replacing the original mask height with FRTM segmentation height, the performance goes up by 2.1%, and the EAO multi-stars goes to 0.481. After replacing DIMP with Super DIMP, we got a performance gain about 1.9%. The EAO multi-stars goes to 0.500. Finally, we increased the resolution of Alpha Refine from 256 by 256 to 384 by 384. Remove corner and mask branch. We get a performance gain of 1%. 1%. The final EAO multi-stars is 0.510. Here are some video demos of our algorithm. It can be seen that our methods can produce very high quality tracking results in terms of both accuracy and robustness. The code of our algorithm have been released. Here's the GitHub link, github.com masterbin IIAU alpha refine. If you want to know more details about the original alpha refine, you can check our paper on the archive. Finally, we also provide a repo for state-of-the-art trackers on various benchmarks. It may be helpful to your comprehension when writing a tracking paper. Here's the link, github.com Wangdong DUT online visual tracking SOTA. That's all my reports today. Thank you for your listening.
Okay, thank you for the presentation. Very nice. Again, so far no questions from the audience and the panelists. So I will ask a few questions, or one question in particular. It seems that the lesson from your presentation is that any tracker that provides a bounding box can be upgraded to a segmentation tracker fairly easily using your head. So do you think that the head unchanged effectively could be used with a broad range of trackers?
Yeah, the base tracker and the refinement module are trained separately, so they do not influence each other. And in this way, our proposed refinement module, alpha refine, can be combined with any existing base trackers. So it has strong it can be used to refine any tracker's performance. So it's it has good general ability.
Yeah. So probably it's like you know that in VOT we have switched from bounding boxes to segmentations, and it seems that now any tracker, if need be, can use a segmentation, could become a segmentation tracker. I think you confirm that the direction is correct. Okay, we have a question from the panelists. The question is, do you use a multi-stage tracking training strategy? Multi-stage training strategy.
No.
Go ahead.
Actually, we do not use any multi-stage training. As I mentioned before, the base tracker and the refinement module are trained separately.
Okay. Okay, so since we have no more questions, thank you for the nice talk. And we will now switch to the third talk in this session, which will be about the winning entry to the long-term tracking challenge. And the talk will be given by Kenan Da. So I can see your screen, Kenan. Nice, thank you. Please go ahead.
Hello, can you hear me?
Yes, we can hear you well.
Okay. Hello, everyone. I'm Kenan Da. I come from Dalian University of Technology. And let me introduce our work in VOT2020 long-term challenge. Compared with short-term tracking, long-term tracking has more challenges, such as longer video, more frequent occlusion, which make its online updates are much more difficult than short-term tracking. We evaluate some popular short-term trackers that need to be updated online. Here I'm just going to list some of them. We evaluate them on long-term dataset and collect their updated information, and we find a phenomenon. When tracking result is good, like this, it has a very high update probability. That's fine. However, when the tracking result is wrong, that means the result has no overlap with the ground truth. It still has a very high update probability. Also, some of these trackers, such as Atom real-time IBNet, has its own update judgment mechanism. That's a problematic. If the tracker learns too many wrong samples, it can impair the ability of the tracker to discriminate it, and it causes cumulative effects makes the tracker perform poorly, especially in longer video. To make online update more accurate, we propose a new meta updater. It can accurately judge whether the current frame is suitable for updating the parameter. In experiment, we provide some kinds of information that is useful for online update. The first is a geometric queue of the target. It refers to the location and size of the target. The second one is describing native queue. It refers to confidence map and response map. Many trackers use this information to judge whether current tracking result is good or not. And we also optimize the appearance queue can also helpful. It's obviously that if we incorporate temporal information into these queues, then we can get more information, such as geometry queue. We can get speed, trajectory, and we can also from appearance queue get appearance change, response map change, and so on. We use two separated networks to encode the response map and image patch of the tracking result into two feature vectors. Then we use LSTM to embed the feature vectors of multiple time steps into a single feature vector, which is further processed by a four connected layers. The final output is a single score, which indicates the confidence of the current tracking results is good or not for online update. And this figure illustrates whether information from a single frame is not enough to judge whether the current tracking result should be used for update. For example, this figure shows the confidence measure output by item on video sequence. We can see that it has to make decisions by the value of score or shape of response map from a single frame, but we can observe some clues from the curves. And this is we visualize the training sample of our metadata. And this is training produce is shown here. Do this produce interactively until the metadata can work with the tracker perfectly. More info can refer to our paper. And this let's see how the updater probability changes after combining metadata. We can see that the updater probability of negative samples dropped significantly, which means that the tracker sample pool is less polluted. At the same time, there are also slightly reduced the updater probability of positive samples, but it's not much. This shows that when a short-term tracker incorporates metadata, it can update well on the long-term dataset. In order to further prove this point, we combine metadata with many recent excellent short-term online update trackers, such as real-time MDNet, Atom, DIM, Precious Deep, Super DIM. And we found that the performance have improved in all datasets, especially in VOT long-term dataset and TLP dataset. It was mentioning that if we combine Super DMP and with our metadata, it can achieve the best result. So it can achieve the best result in VOT2020 long-term challenge. This F-score is over 0.7, which is the best result so far. And also the TLP result is also the best result. And what's more, we also try to combine with other short-term algorithms such as D3S, ECO, MDNet, and all called will be published soon, including training code, test code, and results. Some of them has already available. You can find them in this project. And with metadata tracker, short-term trackers can update well in long-term datasets. But when the text appears, it is still difficult to research it. So we need a global detector to detect the candidate bounding box on the whole image, and then use a verify to verify every candidate box. Some short-term trackers scale estimates are not good, so we also need a bounding box refine. A tracker with the metadata, we call it track at MU. If a track with the metadata global search verifier bounding box refine, then it is a complete long-term tracking algorithm. We call it tracker at LTMU. And this is our LTMU framework. The metadata controls the update of the local tracker and the global detector and verify search the target from the whole image when target is lost. This is the performance on VOT2020 long-term challenge. Compared with DMP at MU improves over 6 points, and DMP at LTMU is a winner tracker. It also has the further improvements, and for Super DMP, this experiment is after VOT challenge. We have achieved the best result in VOT2020 dataset. And what will happen if LTMU is added to Super DMP? I don't know. And this is the difference between this year's long-term winner and the last year long-term winner. Compared with last year winner tracker, this year tracker is much more simple. Many non-essential components has been deleted. The environment is more friendly and there are almost no actual hyperparameters, but it can still achieve comparable performance. That is why I call this tracker baseline long-term tracker with metadata. And last, you can find all the code mentioned in this slide in this project, and you can also find many long-term tracking resources from this code. Thank you.
Okay, thank you for the nice talk. And there is a question from the panel which asks, and it's phrased like, maybe I missed it, but how is the meta updater architecture trained? Is it pre-trained offline? And how do you get the ground truth for that?
The meta updater is trained, meta updater, this training needs to compare, it needs to combine tracker. For example, Atom, you need to use Atom to run on a dataset such as Dassault. You need to run Atom on Dassault and record on result such as bounding box, tracking result image, and response map, confidence score in every frame, every video, and then you use this data to train your metadata, and then you embed your metadata to Atom and this tracker called Atom MU, and you use this Atom MU to run on Dassault to generate 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 results such as funny box, response map, or tracking result image. And to make meta updater, can make meta updater and your tracker can work via each other.
Okay.
Yeah.
Okay, so thank you. We are sort of more or less on time. There are no more questions in the chat. So thank you, Kenan, for the nice talk. And this concludes the first part of the session, and there will be a 5-minute break. Hope to see you all among the attendees in 5 minutes. Thank you. Hello, and welcome back to the VOT ECCV session 2. In this second part of the session, we'll have 2 presentations on the RGB-D thermal winner and the RGB-D depth winner. And without further ado, we'll start by Tianyang Xu. Tianyang Xu, please share your screen and take over.
Okay. Okay. Hello. I'm Tianyang Xu from CVSSP University of Surrey. Here I'm going to share our RGBT tracking approach, DFAT, Decision Fusion Adaptive Tracker. In general, we propose to fuse the RGB and thermal modalities in the decision stage of semi-structure. First of all, I'd like to briefly introduce the development of some RGBT tasks, including RGBT personal ID, RGBT detection, and of course, RGBT face anti-spoofing. Compared with only using the RGB data, these RGBT tasks aim at extracting some complementary information from the infrared channels to support a better pattern retrieval. However, for the RGBT sub-challenge, VOT sub-challenge, especially we don't have enough annotated RGBT sequences for us to train a fully functional network from scratch. Therefore, more attention have been paid on transferring the advanced RGB tracker to construct RGBT tracker. In principle, our DFAT directly use the semi-structure trained from only the RGB data to encode both RGB and the infrared channels. And we also explored different fusion strategies to improve the RGBT tracking performance. For the encoding stage, we employ ResNet50 as our backbone, which is trained from ImageNet and fine-tuned with RGB tracking sequences on the semi-structure. Both the RGB and the thermal channels perform forward pass through the network to obtain multi-layer feature maps, the layer 3 to layer 5. To explore the fusion strategies, we first employ a decomposition method for RGB and thermal image fusion in the pixel level. The fusion method emphasizes multi-layer low-rank decomposition. And from the result of table 1, we can find that a deeper decomposition of pixel level fusion can achieve a better performance. Second, we also perform feature level fusion. Here, spatial and channel attention mechanisms are employed, and we also considered using some max and average pooling operators for these attention vectors. Besides, in the feature level fusion stage, we also proposed to perform channel selection to better highlight the discriminative channels. From the table, we can find that feature level fusion outperforms pixel level fusion, and the proposed channel attention, spatial attention, and channel selection strategies can further improve the performance. Third, we'll also explore the potential of performing decision level fusion. As our baseline tracker Siamese RPM++ is trained only on RGB data, and we observed that the responses of classification branch of the infrared, the thermal channel, are always lower than that from the RGB channels. Therefore, proposed to rescaling the classification scores. In addition, we also introduce learnable weighting parameters lambda here to fuse the responses from the RGB and thermal channels for both classification branch and the regression branch. From the experimental result, we can find that the rescaling and adaptive weighting parameters can improve the tracking performance. Here, we show the framework of our DFAT. So further improvement can be achieved by combining the aforementioned multi-stage fusion strategies. Here, we only perform decision level fusion, and we also considered template update mode using moving average manner for both the RGB and the thermal template. The final results on the RGBT sub-challenge this year is shown in table 5. And the results here is obtained from the Python Toolbox 0.2 version. So maybe some different from the final Toolbox version. We highlight some most important factors in terms of tracking performance in the RGBT tracking. First, the template update can improve the performance. And second, as we use the Siamese network trained only on the RGB data for both RGB and infrared channel feature extraction. And so the scaling output scores can better balance the complementary attributes between these two modalities. Third, a decision level fusion can achieve a better performance than some pixel level and feature level fusion strategies. Finally, I would like to draw the conclusion that it is important to consider the diversity between RGB and TIR data to explore their complementary power. And the RGBT tracking and the RGBT performance would be further improved if we have large RGBT sequences with tracking annotations. Yeah, that's all. Thank you.
Thank you for the presentation. I will ask a question related to data. Have you ever worked with some other data, thermal, besides the one provided in the VOT challenge, or do you yourself plan to acquire some thermal data, or you just picked the challenge because it looked interesting?
Yeah, we didn't use any additional thermal data in the training stage because currently there is highly imbalance between RGB data and thermal data. So we only use RGB data to train our model and propose some fusion method to fuse the infrared channels.
Okay, but maybe my question was also towards the direction, like, why did you get interested in this channel? Are you working with some applications in infrared, or you just picked the challenge because you found it interesting for some other reason?
Yeah, because actually because our group there are other research topic on image fusion. So I think it's there are some connections between the image fusion and the RGBT tracking task.
Okay, okay, thank you. So there's a question from the audience. Many RGBT tasks have used feature level fusion. Do you think that the decision level fusion performs better in the tracking task? And maybe, I think you do. That's, you said it in the talk. So what do you think? Why do you think that the feature level fusion didn't work for you? Tinyang, did you hear the? Yeah, yeah.
Okay,
Okay.
sorry. There's some internet lag, I think. Sorry. Let me check.
Yeah, the question is in the chat window. It's about feature level and decision level fusion. So you were advocating decision level fusion. And why do you think that the feature level fusion doesn't work for you?
Oh, yeah, okay. I understand that. Actually, I think the reason is that, as I said, we only use the RGB data to train our network. So yeah, it's a different modality compared with thermal data. And so the feature extracted from the backbone trained on RGB data cannot accurately encode the thermal data, and this caused the result that feature level fusion cannot achieve a better performance, I think.
Okay, okay, thank you. So there are no more questions. Thank you again for your talk. And let's move to the final talk in this session, which will be given by Li Junwan. It will be on the RGBD challenge.
Hi. Hello, can you hear me?
Yes, thank you, fine.
Yeah, so I will start. I'm Li Junwan from Dalian University of Technology, and in this talk, I would like to introduce our summation titled Accurate Tracking by Category Agnostic Instance Segmentation for RGBD Videos. And please allow me to introduce my co-authors. They are Yiming Wang, Dong Wang, Huchuan Lu from Dalian University of Technology, and Xiangyu Yang from Remark Holdings Incorporations. Unfortunately, the first author, Yiming, cannot make it today, so I will present on behalf of him. We participated in the VOT RGBD challenge, and here's a brief overview of this challenge. The dataset consists of 80 RGBD sequences in total, with diverse scenes and target objects appearance. And the quality of the provided depth maps cannot be 100% perfect, since they are captured by depth sensors. And some of them may have missing regions, while others may be not well aligned with the RGB frames. Besides the common challenging factors in the RGB video tracking, like in-plane or out-of-plane rotation, or scale variation on out-of-view, etc., also exist in this task. The motivation of this work is mainly twofold. In the RGB domain, we observed that the generic object detection trained on large-scale detection dataset is robust to target appearance variations, and the detector output can therefore be used to refine the tracking results. Meanwhile, the detectors can also be used to identify background distractors to prevent tracking drifts. On the depth domain, compared to bounding box-based representations, instance segmentation results provide more precise boundary delineations of the targets, which allow us to obtain accurate target depth based on the segmentation results. So according to these motivations, we propose to leverage category agnostic detection and segmentation for more robust RGBD tracking. This slide shows the pipeline of our method. Our method can roughly divide it into two parts, including the tracking component and the detection segmentation component. The tracking component maintains both a short-term and a long-term appearance model of the target, which together predict an initial tracking results. We then use the object detection results to identify background distractors and to filter out the distractors from the detection results, and which is then used to refine the initial tracking results. Finally, we determine the target state, namely whether it is disappeared or is it reappeared based on the target depth, and the target state is further used to guide the online update of the short-term target appearance model. To be more specific, our tracker is built upon a pre-trained ResNet 18 backbone. Due to the effectiveness and efficiency, we adopt the item tracker to implement our long-term and short-term target appearance models. The short and long-term target models mainly differs from two aspects. First, the long-term model is applied to the whole input images in order to relocate the target after it reappears, while the short-term model operates on our eye region around the previous target center. Second, after initialization in the first frame, the parameters of the long-term model is fixed, while those of the short-term model is updated online to adapt to target appearance variations. Since background noises may be introduced during the online update, so we trust long-term model more than the short-term model. As such, in each frame, if the confidence of the long-term tracker is higher than a predefined threshold, we prefer the tracking result of long-term tracker. Otherwise, the output of the short-term tracker is adopted. For the detection and segmentation part, we adopt the architecture of HTC method, which interweaves instance detection and segmentation to obtain more accurate detection and segmentation results. Well, we pre-train the HTC on the cohort dataset in a category agnostic manner, namely, all objects are treated as foreground category. In order to identify distractors, we label all detected objects of low overlap rates with the target as distractors. And then the top K distractors with the highest detection confidence are selected as the significant distractors, while the rest are treated as insignificant ones. We initialize K item trackers to track the K significant distractors respectively, and mark the location of the insignificant ones as distracting locations. And in the subsequent each frame, we filter out the tracked significant distractors and all distracting locations from the detection results. It also should be noted that the distracting locations are updated in each reliable frames where long-term tracker has higher confidence. Given the filtered detection results, means they have excluded distractors, we compute their overlaps with the tracking results and select the one with the highest overlap as the final detection results. Since the detector often yields more accurate object locations, so we substitute the tracking result with the final detection result if their overlap is higher than a threshold. Otherwise, we will keep the tracking results at the final tracking results. The depth value is mainly used to determine the target states, namely whether the tracking is successful or the target is already lost. To this end, we first compute the median depth value of the target region according to the instance segmentation results. We then leverage a simple heuristic that the variation of depth and area of the target is roughly inversely proportional Based on this intuition, we define the geometric consistency measurement S using the median depth and area of the target, which should not significantly change if the target is not severely occluded or lost. We therefore use this measurement to infer the target state. If its relative variation is higher than a threshold, let's say 30%, we then regard the current tracking result as unreliable, and we will not update the short-term tracker using the current frame. Okay. So we mainly perform experiments on the VOT RGBD dataset to verify our proposed method and compare with the state-of-the-art methods. Our method performs favorably in terms of all the 3 metrics adopted in the VOT RGBD challenge. Additional ablation study further confirms the effectiveness of our proposed techniques, including the detection-based refinement and the combination of short-term and long-term trackers, and also the distractor identification schemes, as well as the depth-based state determination. So our current work has 2 limitations. First, the depth data is only used to determine the target state, and how to take full advantage of depth information for visual tracking is still an open question, especially when the depth map is not perfectly reliable, right? And second, our method incorporates the instant detection and segmentation into visual tracking and currently runs at 1.5 frames per second, which can hardly fulfill the needs of real-time applications. And additional architecture optimization is definitely required. So we would like to leave these 2 limitations for our future work. The source code and pre-trained models are publicly available in GitHub. So if you are interested in our work, please refer to the source code for more implementation details. That's all, thanks.
Okay, thank you. Thank you for the nice talk. There are so far no questions from the panel, from the attendees. I must admit that I had some questions, but you actually answered them on the last slides. You spoke about speed and the ablation study. If you could show that slide about the ablation study, it seems that the detection is by far the most important improvement, or I think it's significant, I would say.
Yeah. That is correct. We find the detection based tracking refinement plays a very important role in improving the final results.
Mm-hmm. So it's quite interesting that if we look at these winners of all the challenges, and you are the last one, everyone picks some particular component, refined segmentation, update rule, redetection, to achieve a significant improvement over the baseline. So one can think about combining these things. So, okay, I think that the presentation was clear, and if there's no more questions from the audience, I think I will conclude this session. Thank you for the talk again.
Thanks.
In a few moments, thank you. And in a few moments, we'll start with the panel, which will be chaired by Michael Felsberg. So I'm handing over to him. Thank you to all those who attended and enjoyed the talk. Thank you.
Yeah, thank you, Jiri. And oh, I see my background model is very bad now at the different lighting conditions. Sorry. So I ask all winners still present and Jiri to join the panel. And if possible, switch on your video so that we can see you while you're answering the questions. Okay. So let's see whether everybody is visible. I think we lost one of the winners on the way. Well, we will go ahead anyway because we are, oh, I can see now, Binyan, he has lost his internet connection. Mate, can you add him again to the panels, to the panel, please?
Yes, I've already done it, so he should pop up soon.
Yes, now he's with us. Could you please turn on your microphone and camera? Yeah, or actually, in the panel we can keep the microphones open. If we have problems with the sound, I will ask you to mute your microphones if you're not speaking. In my experience, it otherwise happens that people start to speak without switching on the microphone. Okay, so then I guess we are ready, and I would like to throw one first question into this round. And maybe this is the question that we in the committee ask ourselves each year. So what would you like to change in VOT? Who wants to start? You can just start to speak. Don't need to lift your hand. There's a function there, but we don't use that. Just go ahead, please.
This is a question for the winners of the challenges, because as a member of the committee, I know what we are planning, what we think might be improved, but perhaps we would like to see feedback, and the audience can say something as well in the chat, the attendees. But mainly the winners, you have played with the data, with the engine, evaluation data sets, anything that you would like to see changed, maybe to make the thing more difficult, easier to use, or whatever comes to your mind.
So if a question or comment pops up from the audience, I will take it up from the chat. I also would like to mention Kenan doesn't have a camera at hand, so this is why he's not visible, but we can hear you, I guess. So the most recent channels are the multimodal channels. So these are youngest ones. What would you like to change in those? RGBD, RGBT?
Actually, I have some thoughts. I don't quite familiar with the other challenges, but for the RGBD challenge, it seems that all the test video sequences are available to the competitors. So I think one more common way to evaluate the performance is to unrelease the testing data, only release some training data or some validation data. So so we can submit our pre-trained models to the website and to evaluate on the test data. Therefore, maybe the comparison may be more fair in this way. I don't know if I make my points clear.
Yeah, it's clear. It's what we had this request and suggestion for short-term tracking maybe 5 years back, and we introduced a sequester data set. It's clear the benefits. It has some the problems with that, or problems. Okay, it's indeed better because we spot overfitting on the data. But we need to do two things: calculate ourselves a lot of results, which cost computing power, and we have to annotate roughly double the amount of data. So, but okay, it's a suggestion, and the curator of the RGBD data set will be notified, and maybe we will try to do that, because indeed this is interesting.
Yeah, thank you for the suggestion or the comment, and also the explanation from Jiri. There is actually one comment from Dong Wang, who says there's no camera motion in the RGBD. So is this actually true that all the sequences are static?
Okay, that's clearly a mistake on the design, because things like background subtraction methods would almost work for that. So okay, point taken, and we have to update the data set on that.
Okay, other things you would like to change in VOT? Otherwise, we could go to the next question.
I have a piece of suggestions for VOT real-time challenge.
For the real-time challenge, okay.
Because in the current sightings, different participants may use different type of GPU. They may use different type of disk. Different type of disk may influence the I/O speed. Then influencing the tracker's speed. So maybe the VOT committee may consider use more eco experiment sightings for different participants. I mean, maybe requires the participants use the same type of GPU or compute time consumption excluding the influence of I/O speed, and only take the time consumed on tracking itself. That's what I want to say.
We have Luca. I see the window. I'm not sure whether he's attending, but when we verify,
Yeah, I'm here.
Luca, when we verify that something is indeed real time, do we do any independent tests, or we just leave it to the participants?
So we don't verify real time in any way. No. I mean,
So,
this is not really up to me, I guess. Also.
Yeah, it's complex. So I think that my thinking about the real-time challenge is that we started it when the winners were running like very, very slowly. And these days, the winners of the overall challenges are quite fast. So, okay, you heard the last winner for the RGBD was saying, okay, it runs 1 frame a second, which is still okay compared to what we had 3 years back, where something was running 40 seconds a frame. So, and I'm not sure you are the winners. I don't remember the exact times, but speeds like 20, 30 FPS among the winning entries show up. So maybe the real-time challenge becomes, it might have been rephrased like, I don't know, real-time performance on some piece of hardware, because speed is always needed if you do something on the Raspberry Pi embedded systems. There are hardware architectures which will not have a strong GPU, but it's becoming less of a pressing problem. The best entries are near real time anyway on some hardware. So it's more about the hardware requirement. So maybe the RT challenge for me is the one. We don't want to have a proliferation of challenges. Maybe the RT challenge will not be run. I think it will be not run. We might say something like the best method, which does not require a hugely powerful graphics card or something like that, because it's very difficult to define exactly the hardware environment so that it's fair.
Okay, thank you, Jiri. Other suggestions and wishes, what you would like to change?
In terms of the tracking speed, I think maybe we can involve the flops for tracking each frame to balance the impact from the hardware.
Well, is it so easy to calculate things like graphics card performance into flops, and that certain things are parallelizable easily on the GPU, some other things are not? It's difficult. I'm not, yeah. I think it's a difficult problem.
Okay, we have one more question here from the audience, and I think it is implicitly answering or related to the question what to change in VOT. It is about the anchor frames, and some of them seem to be noisy. I'm not quite sure what do you mean by noisy in your question here?
Maybe the segmentation is not that good at the anchor frames, or yeah.
Is that what you mean? That the accuracy?
Yeah.
Maybe we have to wait for the feedback here.
Yeah.
In the meantime, I would like to proceed to the next question. We can return to this about the anchor frames, the related questions later also. So a second question which I would like to ask the panel is, which functionalities would you like to have in the toolkit? What would it make more useful? So the toolkit is perfect.
Mm-hmm.
Okay, while you think about this question, we return to the previous from the audience. Now there's a clarification. It's about occluded anchors and blurry objects in the anchors. So I understand that the anchors are chosen such that it's very difficult to start the tracking from that particular anchor.
It actually touches a bias that we have in tracking sequences, that often, at least in the initial frame, the object is in a canonical view, sort of like highly visible, maybe larger scale, and so on. And perhaps, okay, it's an issue whether we should not have even the starting frames partially occluded. It is a scenario where you want to try to track something from a frame where the object or target is not fully visible. So highly occluded is probably not a good idea, at least for short-term tracking. But yeah, it's interesting thing, and we should have a clear strategy. Okay, I will translate this to something that the VOT committee can discuss, which is what is the requirement for some frame to be eligible to become an anchor. Yeah, so obviously an anchor frame where the thing is completely occluded makes no sense, and so we might say there is a minimal requirement for something to be an anchor.
Just as clarification, so this is about the anchors for reinitialization, not the initial one for the start of the tracking.
Yes, but that is in some sense not different than the others. It's not, and yeah, because yeah.
Okay, there is a question by Kenan. You can also formulate it yourself if you want to.
Okay. If we use VOT toolkit, we will in MATLAB version it's not convenient to evaluate result as your code is complete with Python. And okay, I hope you took it just took it evaluation module can just like a package which we can import in Python and we can evaluate the result without any restriction. We just have a result and we can evaluate the results.
Okay, so if I may repeat the suggestion, so what you say is it would be desirable to have a simplified set to use the toolkit for evaluating your tracker without complicated configuration of your tracker. Is that what you want to suggest?
Yeah.
Yeah, if I might, so I know what he's saying, and just open like an issue, and we will fix this. Yeah, it's true.
Okay, maybe we can proceed to the next question. So this question is open, of course, also to everybody, but maybe Jiri has a special opinion on this. How do you see the relation of VOT to other challenges like MOD-TOW and UAV tracking?
So I had a talk at TAO and I saw the whole workshop, and I think that in TAO it's really about object tracking. So by object I mean things which have a name, car, bike, whereas here we like to track a target. The target doesn't have to be an object, it could be part of ground, wall. It's true that most of our, or many of our objects in VOT are, the targets are mainly objects, but they need not be. So, and it's very closely related to things like, they are interested in, what they would like to have is activity recognition, action recognition, object detection together with tracking. So they're interested in tracking as part of high-level description of the video, whereas we think more about being able to follow an emotion without prior, for instance, restriction that the thing that is moving is from a known class. I think this visual object segmentation challenges like Davis, they are converging with what we are doing. You could see that the result, the winner of the short-term tracking provided a very good segmentation. And I think the segmentations are comparable with the visual object segmentation results. And maybe it turns out that I think our data set is richer. And some other data sets and benchmarks, they try to impress by the scale or size of the data set. And what we try to be here is diverse and efficient. So we would like to have say, the smallest data set which will allow you to benchmark. So we separate between benchmarking activities and learning your trackers. You can perhaps learn trackers on some other data sets, but on our data set, you should learn your weaknesses efficiently, which means by not running over thousands of videos. So I think that's how I see it. Of course, I think after this ECCV, we should review the data sets used, because I had a talk in the drone workshop. It was called This Drone, and they also had a tracking challenge, and it was quite interesting data, something like tracking sheep, for instance, from a drone flying above a herd and things like that. So there are always interesting data coming from different domains, and what we are trying to be is general and diverse and cover most of the corners. So I would say, but at least 2 or 3 tracking challenges were run in conjunction with ECCV besides VOT. So, okay, sometimes competition is good because it keeps us agile, and that's why we have to react to the community requests and make decisions so that results of the VOT are informative to the authors and also to the community. If you get a good result in VOT, the tracker will work well in a broad range of applications. That's what we would like to achieve.
Maybe one of the winners who would like to say something about the relation of VOT to other challenges? including video object segmentation and maybe video instance segmentation? Or let me put the question slightly differently. It took us quite some time to move from bounding boxes to segmentation, and this leads to certain convergence to the video object segmentation, as Jiri said. But what would be the next step? Should we go for 3D models, reconstruction, estimation of parameters of objects? Should we or should we not? Should we stay that general, just based on the appearance, or should we go to something else? Should we combine things, or should we leave this to other challenges? What do you think? What would you make attending in more challenges? What would make you maybe prevent from publishing a paper due to the challenges?
Yeah, for this question, maybe I think this can be connected to your second question for the toolkit. And I think currently the toolkit is just used for evaluation the VOT challenge, and we always use this in our paper. I don't know if it is possible to improve the toolkit so that it can also evaluate other data sets from the OTB to the recent TrackNet layout. Maybe you can use the VOT protocol to evaluate other data set. So maybe because in my opinion, the current anchor-based evaluation toolkit is more stable. I think it's more robust to evaluate tracker's performance. So maybe it can also be applied to other data sets.
Mm-hmm. Okay, this is an interesting idea. So you are saying, like, okay, connect our protocol with the different data sets using their annotations and show the superiority maybe or the suitability of the VOT methodology for other data sets, which maybe use just, I don't know, some simple average overlap or something like that. Okay, that's a good idea.
Further comments?
Yeah, I think maybe 2D images may not be enough for the computers to perceive the context of the real world. And I think the VOT RGBD challenge actually gave us a very good directions to transit from 2D images to 3D 3D information of the scene. So maybe we can in the following challenges, maybe we can move forward along these directions to maybe take like point clouds or other 3D informations to focus on the task of maybe 3D object tracking or something like that.
So you suggest to go from RGBD, which is in a sense 2.5D, to full 3D tracking?
Yes, yeah.
One question here from, well, actually not from the audience, but anyway, what kind of objects would you like to see in the new RGBD data sets? I noticed that time is running up, but I think this is an interesting question. So we should consider this for a second, and maybe we get a nice suggestion. But then we will also slowly round up the discussion. Maybe it's also worthwhile to say that any idea, suggestion, whatever you have, you're always welcome to send an email to the committee and provide your suggestion offline afterwards. Might be that this question came a bit unprepared, and it's maybe not that obvious to put into the data set. Okay. No immediate ideas? I mean, the question implies a bit like beyond the type of objects that are already in RGBD.
Okay, for this question, maybe I think maybe you can involve some transparent object here, like a bottle of glass of water, so that from the RGB channel, it is not that salient. Mm-hmm. And for depth channel, it may be, it can be highlighted in the depth channel.
So you mean that the RGB and the depth are inconsistent? Mm-hmm. Yeah, there's some suggestion, some animals, pets. Yeah, that's always popular. There's also a further comment by Canon when it comes to the future of VOT, and I think this is an interesting suggestion. He says that VOT should put more emphasis on the attributes of tracking, such as obvious changes in targets and tasks that are difficult to complete with one-shot detection. So that means tasks where you really need to track over time rather than just run the detector on the frame. Canon, if I get this correctly. Okay, guys, we already ran over a few minutes, and I would like to give you the opportunity to say some last words. If you have something more to add that was not matching any of the questions, but that is related to the VOT challenge. Okay, that doesn't seem to be the case. So this brings us to the end of the panel discussion. I thank you all for participating. I know this is already a challenge in real life, but in a virtual panel, it's maybe even more laborious to give answers to these questions. So thank you very much. And the last point on the agenda is to round up. I'm not sure, Mate, will you do that?
That's all right. You can wrap up, and we'll finish with that.
Okay, so then I will wrap up, and I would like to thank everybody who contributed, all the submissions, on all the attendees of the workshop. But in particular, I would like to thank Mate again for pulling all this together and making this challenge possible for the 8th time. And I'm looking already forward to the 9th challenge and next year. So hope to see you all there at the 9th challenge next year. Goodbye.